Yeah, good afternoon, everyone. Welcome back. We are having a GFL seminar after a while. Today we have with us Ankita Kannad. She is a graduate student, PhD student at the Scripps Institute of Oceanography, working with Jen McKinnon and Janet Sprinter at Scripps Institute. She does upper ocean observations, their influence on the monsoon, and other related phenomena. It is going to be telling us about her research.
Thank you. Hi, everyone. Like Penny said, I'm a fifth-year graduate student at the Scripps Institution of Oceanography, and this is what has been done as part of a program called OceanSat that's trying to understand the influence of uh, the ocean on the onset of the summer monsoon in the ocean. Um, and again, this is a broad audience with many different scientific backgrounds. So if you have any questions, please feel free to stop me. And so I'll start with a brief introduction on what stratified turbulence is in the ocean, why it's important, and then move into kind of talking about turbulent mixing in the surface boundary layer, which is part of the focus of my research and the study, and then look at specifically the case study of the South Asian Summer Monsoon. And this is what is currently being written up in a paper. Okay, so starting with sort of stratified turbulence in the ocean. So as you all probably know, the ocean plays an important role in the global climate as a kind of vehicle of heat. It transports heat from the poles to the equator. And this schematic here kind of shows you the broad scale mean currents of this flow. But if you look more closely at this flow, and this is from an OSCA surface current product using satellite data, you can see a very rich turbulent structure. And a lot of work in recent years has gone into trying and understanding why this might mean and why this is important. Sorry. And one of the kind of key studies that came out of trying to understand this was looking at the role of these turbulent processes in driving the overturning circulation. And that was work that was done by Walter Monk in the 1960s and continued to be done with collaborators and in recent years by other scientists as well. So the question that they had and the problem that they had was that you had all of this water that was being transported to the poles, as I showed you, cooling and descending into the abyssal ocean, and then being transported towards the equator. And you have this problem of how all of this water that's being transported is being upwelled. And so they started with this idea that this upwelling happens through a downward flux of heat through turbulent mixing. And so that turbulent heat flux then causes this abyssal dense cold water to gain potential energy and rise. And that's sort of shown by this kind of simple equation here, showing you the vertical attraction of buoyancy being balanced by this diffusion of buoyancy into the ocean. And so how much mixing do we actually need for this process to occur? And so through some sort of simple arguments, they were able to say that we needed about 2 terawatts of power going into providing that potential energy to drive the overturning circulation. And they were able to show that this was roughly how much energy was going into internal waves in the ocean. So you've probably all seen surface gravity waves in the surface of the ocean. You have very similar processes because the ocean is stratified. You have these internal waves, and there's many ways in which they are generated, but the main drivers that they found were through wind, through near inertial oscillations. So that's when the wind pushes on the ocean, causes it to oscillate, and that then generates internal waves, or through the interaction of barotropic tide with the surface bathymetry. And so this idea that they started with was that the breaking of internal waves in the interior ocean was what was mostly driving the turbulent mixing in the ocean interior. And so if you kind of look at this and go out and measure shear, which is sort of an indicator of velocity fluctuations, and then there's turbulence, which is what is shown here, you can see over these kind of scales from small scales to large scales to small scales, you see this kind of energy cascade from the production of turbulence and internal waves. It's sort of nonlinear interactions that then cascades to a level kind of defined by this Osmedov scale where you get 3D turbulence. So this is turbulence that now is no longer feeling the effects of stratification. And then eventually you can get cascade down to scales that are at levels at which molecular processes become important, and you get a viscous dissipation. Now, if you kind of go out and look at this sort of budget of energy going into the ocean, only a very small portion of that surface forcing and tides is a different situation, but let's just talk about surface forcing. Only a very small portion of that power is actually transferred to internal waves. And most of that power is dissipated in the surface boundary layer, which is, if you kind of look at this schematic, which is very busy, but if you just look at sort of a zoomed in version of it, the power that's going from the waves into the ocean is 70 terawatts. Only a small portion of that goes into internal waves, which is 0.2, and the rest of it is sort of driving, mixing in the surface boundary layer. So as you can imagine, the surface boundary layer is a very important region of the ocean that kind of characterizes this interaction between the atmosphere and the subsurface. And this is a kind of a brief schematic of sort of all of the processes that go into it. It's a fairly complicated region of the ocean, but it's generally characterized by this very well-mixed layer. It's a very uniform density, and that's driven by a ton of surface forcing from winds, waves, as well as buoyancy effects. You have sort of surface cooling of the ocean. And I'll kind of talk through this a bit more in detail in the next few slides. And we can kind of think about this surface process as a kind of balance of turbulent kinetic energy. So this is probably fluid mechanics people, probably equations you've seen before. But generally, you can think of turbulent kinetic energy as a balance of its production, its transport. So the production terms are shown in orange and blue, and its transport, which is shown in purple, and then its dissipation through molecular processes. And so you can kind of summarize that into these kind of these letters that I have done here. Generally, we kind of assume that this turbulence is happening in a sort of steady state condition, and that the transport is almost negligible. So you end up, the physics that we really think about is sort of this balance between the production of turbulence and then its dissipation. And so kind of walking through those different terms, one way in which you can produce turbulent kinetic energy is through shear. So this equation is maybe something you've seen before. It's telling you that these turbulent processes are producing, turbulent processes produce kinetic energy through their interaction with the shear of the mean flow. And this mean flow can either be generated by the wind, which is this term here, or it can be generated by waves through the formation of Stokes strips. This is sort of a horizontal drift of the waves over time. And so that can generate shear instabilities that then cascade into smaller and smaller eddies and then into dissipation. So that's one way in which you can, yes.
UH and US levels to velocity.
Yeah, so the UH is just the horizontal shear from the wind, and the US is this, so the Stokes drift really just drives a horizontal shear very close to the surface.
Inside the ocean.
Yeah, it's sort of scaled by the wavelength of the surface gravity waves. And so very, very close to the surface, you see very high shear because of the Stokes drift. And then as you go deeper, it really becomes a dominant wind-driven shear that dominates the mixing. Another way in which you can produce turbulence is if you have a situation where you have surface cooling. So in that case, you have basically an upward transport of buoyancy, right? You've got cooler water at the surface. You want to have an upward, and that's unstable. So you have a situation where you need to transport up warmer water, relatively warmer water from below. And so that creates a production of turbulent kinetic energy through convection. And that's sort of that buoyancy circle here that also drives mixing. And then finally, you have all of these processes then eventually cascade to these small scales that I showed you earlier in the spectra. And then you reach sort of this levels where there's resistance dissipation by molecular processes. And something that this equation doesn't fully capture is also that these processes then interact with the subsurface ocean. And so they can then drive an entrainment or sort of mixing of this denser water from below. So the upper ocean is sort of characterized by this unstratified mixed layer, and then until it hits this sort of really stratified pycnocline. And so that interaction between the pycnocline then determines how much momentum gets transported into the ocean interior. And it also, that mixing also causes this, the surface boundary layer to also get denser and so deepen as well in the process. And why I'm sort of going into this detail is because we don't actually really fully understand these processes, and also are not fully able to resolve them in models. And so you get, in many cases, a bias in mixed layer depth and sea surface temperature, which then, as you might expect, impacts processes like the monsoon, which in one of the main drivers of it is sea interactions. And so, as you can see, in like the Indian Ocean, for example, so some of that bias can be close to 60 meters, and so it's quite significant. And so, like I mentioned, we have all of these biases in our model. We want to improve that, and that was sort of the main goal of this ACOMSAT project that I will be talking about. Was trying to really look at these boundary layer processes both in the ocean and the atmosphere in detail, and try to understand where we might be kind of going wrong in our models in predicting the onset of the monsoon. This is not the first time this work has been done. People have been thinking about these questions, and particularly in the Bay of Bengal for a very long time. Some people in this room as well who've been working on this problem. And one of the observations that came out of this study was a mooring that was equipped with tripods. So these are sensors that give you turbulent mixing, and they have them at different depths along this mooring, so you could get sort of the depth profile of mixing. And they also had surface atmospheric conditions, and so they sort of had this deployed for a year, the year of 2014. And so they got a sort of seasonal cycle of what mixing looked like in the ocean, in the Bay of Bengal during this time. And so you can see here, the top two panels tell you the atmospheric conditions. So this is wind stress, this is precipitation. And the colors show you the period of the winter monsoon. The green shows you the transition, and then the blue shows you the summer monsoon. And so the winter monsoon, as you can expect, is a period where there's a peak in wind strength, right? The winds are strengthening. They're sort of in this northeast direction, or coming from the northeast. And probably here in Chennai, you get a lot of rain. And then similarly, in the summer monsoon, you can see a strengthening of the winds and you get a lot of precipitation as a consequence of that. There's some variability in the surface heat flux. So positive values show you warming of the ocean surface, negative values show you cooling. But the sort of key point here is that there's a net warming during this transition period. And if you kind of look at the surface temperature of the ocean, it sort of follows that pattern, where there's cooling during the winter monsoon, there's a net warming during this transition period, then it cools again during the summer monsoon. And corresponding to this cooling, you look at the kind of heat that's transported by turbulent processes. How to actually get this value, I'll talk about a little bit later because I do this calculation with our measurements. But you can see that there's a peak in this turbulent heat flux into the ocean, driving a cooling of the boundary layer during the winter monsoon and the summer monsoon. And again, the same positive negative applies. And so if you kind of go and integrate this heat fluxes for the surface and the turbulent heat fluxes from their measurements over the northeast monsoon, which is the winter monsoon, and then the summer monsoon. The winter monsoon is fairly weak signal, but if you see in the summer monsoon, the net heat fluxes are on order of 30 watts per meter squared, and there's a net cooling from turbulent heat fluxes of an order minus 22. So the turbulent mixing effectively is sort of similar order of magnitude to the amount of heat, the net warming that happens during the southwest monsoon in this particular year. And so they were able to show that turbulent mixing is potentially an important driver of upper ocean cooling during the monsoon as well. Now you might notice that this transition period, this green layer here, is a period with very low turbulent heat fluxes. So one is that maybe it's just a quiet period, there isn't a lot of mixing. And other is that maybe the spacing that they had of these turbulent sensors in the mooring was maybe not potentially sufficient to kind of capture the processes that were happening in the monsoon transition. And so that was something that the SACMSAT project, as I mentioned, was interested in going and investigating a little bit more. And so we, compared to the mooring, which was a little bit further north, we were measuring right off of the close to Chennai. We actually traveled from Chennai on our ship, measured the sort of southeast and Bay of Bengal period. And we measured the period of the monsoon transition, which was approximately from April to mid-June. And I'll talk a little bit about these panels later on. And then one thing that we were able to do with this year's experiment was to actually go out and profile turbulence. So rather than having a mooring, that's a sort of stationary location with measurements of turbulence, what we were able to do was have this instrument called the mod accelerometer that's deployed from a winch system that basically just drives this profile up and down in the ocean. So you get sort of continuous profiles as the ship is slowly drifting around 1 or 2 knots. So this mod accelerometer, right at the base of it, has 2 probes, one a fast thermistor and a shear probe. I'll just talk about the shear probes, but since if people are interested, the fast thermistor measures these very fast temperature fluctuations as this probe descends as the profiler descends in the water, and so from that you can get a measure of the dissipation rate of temperature variance, or chi. And then the shear probes, which are measurements that I'll actually show, similarly do that with velocity fluctuations. So you can get a measure of epsilon, or dissipation rate of turbulent kinetic energy from that. There's some things that are sort of
Sorry to interrupt. There's a mobile here. Was it there?
this one.
So. I had direction before, so I put it on. Thanks, sir. Sorry to disturb.
No.
Yeah. Thanks.
Yeah, and so there's two ways in which we try to reduce noise in our instrument. One is by having this profiling happen on a boom that extends out far away from the ship, because the ship wake generates its own turbulence, and so we want to avoid that. So that's one way, and the other is through this sort of umbrella kind of feature that we have, which is shown in this picture here. And so as this profiler sort of prefawns, it causes this umbrella to rise, and that sort of slows its descent as well. And so that kind of reduces the vibration of the instruments. And so helps you get a better measure of turbulence. And from this, you can get a shear wave number spectra. And this is an example of one from the mod epsilometer. And so the level, as you can see here, this is the shear spectra in wave number space. And the colored values show you different measurements of dissipation rate of turbulent kinetic energy, or epsilon. You can see that the higher levels of this shear spectra, the higher levels of epsilon are. And this particular profiler, because it has such a high sampling rate, it's about 325 hertz, it's able to get both this sort of the whole kind of evolution of spectra and this 3D turbulence space from the sort of inertial subrange, which has this characteristic positive 1/3 slope, and then sort of the viscous roll off at higher wave numbers.
Ankita,
Yes.
Cycles per meter,
Yes.
so 100 would be 1 second.
Yeah. So the roll off, usually our noise floor is about a centimeter. So we sort of integrate across basically where you hit the noise floor, which is usually where the spectrum goes up. And so that's usually approximately the resolution you get.
Yeah, this is very interesting. Please explain the tolerance for.
Yeah. So this is usually a technique we use to check the measurements, is to bin these spectra by the corresponding kind of epsilon value. And so this is the sort of highly vibrating spectra is the measurement, and then the solid line is the theoretical spectra, and this just to show that it matches it well. And then this dotted line here shows you the noise flow, which is basically they do a test of this instrument, so the sensitivity of it in the lab, and so they get a noise flow from the lab, and they sort of subtract that from the spectra. So, this is sort of the edge of the measurable spectra that we can get out of this instrument.
Also, these are different profiles taken at this test.
Yeah. This was our actual measurements are quite variable, because we have periods where there's strong mixing, and this was, I think, taken from a short cruise that they did to test this instrument. So it's generally high levels of mixing. It's a similar period of time. Yeah. And then just to point out the typical resolution of measurements that we get from profiling, so typical CTD, which measures temperature, salinity, or an ADCP, which measures ocean currents, which is another way you can get turbulence. Those are generally at much lower wave numbers, much higher scales compared to this instrument. So you really do need to measure at a very high sampling rate to get the kind of measurements that we need to get turbulence. Okay, so now kind of painting a sort of broader picture of what the monsoon transition looks like. And this is from measurements from a moored buoy that was close to our site. This is wind speed, wind direction, and then surface temperature. So very similar to that Warner paper, which was from 2014, this 2024 monsoon transition was characterized by very low wind speeds for several months, so from March to almost mid-June. And this period corresponded to this sort of long-term warming of the surface ocean. You also see these peaks, and if you kind of zoom in into those measurements, you'll see that there's sort of a diurnal cycle to the warming. So there's peak warming in midday, and then it cools at night, and again warms at midday. And this is characteristic of a surface ocean feature called the diurnal warm layer. And so diurnal warming can thermally re-stratify the ocean. So it can cause stratification to form just by creating a very strong gradient of temperature. And these typically form under weak winds and strong atmospheric warming. So you need to have relatively weak wind forcing for these to form. And because of this strong near surface stratification, it traps wind momentum, and so it can both trap heat as well as wind momentum. And so over time, it develops shear instabilities that then break and cause a deepening of that mixed layer. And then eventually you get to a point in the day. So the schematic shows you sort of that trajectory of temperature. You get to a point in the day where the surface ocean starts cooling as the sun disappears. And so you start getting these bigger activities that form as the surface destabilizes. And the schematic also kind of shows you the wind speed, these sort of arrows and you can see that where there's this temperature gradient, you see a peak in the wind speeds as well. The surface currents as well, showing you that sort of trapping of the surface momentum when the diurnal warm layer is present.
It's a nice figure. Doesn't tell you what depth we're looking at.
Oh, yeah. I will have an example of that next, but it's usually about 10 meters. Yeah. But in our case, we saw it much deeper diurnal warm layers as well. So, and then after this sort of warming diurnal warm layer period, we experienced a cyclone. So that figure there shows you the change in sea surface temperature. So the cyclone creates upwelling and then net cooling. And the red line shows you the sort of path of the cyclone. So we were really at the onset of the cyclone. And so it was really just a low pressure system where we were. And then it became a cyclone as it went further north in the basin. But we did see a peak in winds as a result of that. And then following that cyclone, let's shift to the winds blowing towards the northeast, which is characteristic of the summer monsoon. We also saw cooling of the surface as well. So in addition to the morning, we actually kind of captured this atmospheric and ocean transition with our shipboard profiling. And so this is showing you again wind speed. Now we also have measurements of precipitation at surface heat flux, the surface temperature, which is now about 4 meters, and a boundary layer depth. And you can see, similar to the mooring, there's this period of pre-monsoon, weak winds, strong surface, or actually pretty negative or close to zero surface heat flux and low precipitation. And then you get to the cyclone where the winds pick up. There's several rain events. There's a net cooling. And this is where you see a net cooling in temperature as well, the biggest cooling in temperature. And then again, after this sort of strong wind event, we go back to conditions similar to the pre-monsoon, where the winds reach similar levels. There's a net warming of the surface ocean, and you sort of start seeing these diurnal peaks of the temperature as well. And then we, as always happens when you do one of these field campaigns, we left almost right before the sort of real active phase of the monsoon kicked in, was sort of the end of our field measurements. And so we mostly just got the sort of transition into this, the transition into this sort of strengthening winds of a more active phase of the monsoon. And so all of this is just to say that there was a lot happening during this period. There was a lot of variable atmospheric forcing, but the net effect was that the boundary layer cooled and it deepened. And so the kind of two big questions that we tried to address with the study was, one, trying to understand what surface forcing was driving this boundary layer deepening. And two, we have these sort of restratifying periods, one before a strong wind event and one after. So what role this sort of period of very calm, dry and warm layer kind of conditions, how does that influence boundary layer deepening or entrainment as well? And so before we kind of dive into those questions, just kind of walking through our actual profile. So what did we actually see? So in the pre-monsoon, the top plot panel is just the surface conditions. So again, it was weak winds, and there's still some diurnal cycle in the surface heat flux. And in temperature, and the next panel is temperature, which, as you can see here, and the black shows you the depth of the boundary layer, basically a condition of almost constant density, a layer defined by almost a constant density. And then the gray line shows you the isothermal layer, so a layer of almost constant temperature. And in the pre-monsoon, there's a difference between where there's a layer of constant density and where there's a layer of constant temperature because of a salinity gradient. And that salinity gradient actually compensates for a warmer subsurface, which otherwise would be an unstable condition in the ocean. And so you have what is the formation of a temperature inversion. And on top of that temperature inversion is also a sort of diurnal cycle of deepening of the boundary layer as well. And you see that again in stratification, which is a function of the density gradient of the profile. You also see relatively high shear within this boundary layer from our current measurements. And as you would expect, there's higher dissipation within this boundary layer. That sort of is where all of that mixing is happening. And then it weakens considerably as you go below that. Now, if you go into the cyclone period, there's strong winds, there's net cooling. There's a net cooling of the upper boundary layer as well, kind of again defined by that region within the black line. And there's higher subsurface shear at the base of the mixed layer, because now you have winds that are driving these inertial oscillations, and this rotation creates shear at the base of the boundary. And now you no longer have a sort of diurnal deepening of the boundary layer. Now, because of that strong wind forcing, you have mixing throughout the day. And so you can kind of see that in our dissipation measurements as well. And then right after the monsoon, the cyclone, we returned to a sort of period of weak winds. And so you can see that in the temperature, again, you have the surface warming that then it is deepened, that warming signal is seen deeper as you go over the course of the day. And that deepens until it hits this very strong stratification, which defines the subsurface tectocline, so the subsurface stratified layer. And something that happens as that schematic showed is that this surface warming or the surface stratification traps wind momentum. And so it can also trap, and you can see that in shear as well. So you can see the high shear from the wind momentum that is then also mixed down over the course of the day.
That's from which instrument?
This is all from the accelerometer as well. It had a CDV, so it was measuring temperature and salinity concurrently with mixing. And then finally, the monsoon period, it sort of shows up very clearly in shear, but you see the kind of a relatively weak diurnal warm layer forming that then transitions to this period of well-mixed boundary layers throughout the day as the winds strengthen. And so kind of condensing all of that into a few different regimes. So you have the pre-monsoon regime, where you have these shallow diurnal warm layers forming during the day over a temperature inversion, and that gets eroded relatively quickly, and then you have a sort of erosion of the temperature inversion at night. So that's sort of the pre-monsoon period. And I forgot to mention, but I've just taken 2-day chunks of these measurements. So this is just to kind of highlight a kind of characteristic day. Obviously, there's spatial gradients and things that we were also going over on the ship. So I was trying to pick a period where there wasn't too much of that. And then during the cyclone, basically all of that subsurface structure and temperatures been mixed away. And so you just have these strong winds driving mixing throughout the day. Oh, sorry. And then in the recovery period, which is again a return to these sort of calmer conditions, you see again a formation of a diurnal warm layer, but that continues to deepen until it hits this really strong stratification. And you also see this period being a period with higher shear at the base of the mixed layer, and so potential driver of internal waves. So yeah, so going back to sort of this question of what processes drive this boundary layer deepening, a typical approach to this is to look at turbulent scalings. So this is kind of what would be expected profiles of dissipation if you had a wind-driven event, wind-driven dissipation waves or buoyancy. And so going back to that schematic, and now we'll just look at the sort of characteristic dissipation profile. And so for convection, which is when you have surface cooling, you have this convective eddy forming, a typical scaling that aligns well with measurements is to think of dissipation being just a uniform profile that's equivalent to the surface buoyancy flux. So whatever surface buoyancy from atmospheric forcing is then just transported across the ocean. And so it's just this vertical line that generally corresponds well to the sort of middle of the mixed layer, as you see here. So you have all of these processes at the surface that are much higher dissipation. And that's generally driven by wind, which has this sort of 1 over depth Z or 1 over depth relationship. And also relates to a friction velocity, which is a sort of measure of the wind stress on the ocean. And in our case, because we didn't have great wave spectra to get Stokes drift, we just sort of infer enhanced dissipation relative to the wind scaling. So wherever there's higher dissipation relative to the wind, we just kind of assume that corresponds to the influence of waves on the ocean. And you can kind of see that here, where they sort of show this D minus 4th relationship that's sort of typical of a wave-driven turbulence in the ocean.
So
So,
you say they've done gaming language turbulence here?
yeah, so there's yes, that's right. Yeah, the actually both. So there's wave breaking, so there's turbulence as a result of the breaking of the waves, and the shear that causes strokes. That shear in the stroke strip profile is then thought to drive a line here.
It's not going to be much surface wave breaking in the deep ocean.
No, yeah,
So it's mostly just level wave.
should mostly be
Then where's the current coming from? Here?
the.
Is there a main current in this location?
We tried to pick a location that was relatively quiet. So based
So
on
it's only closed drift. There's no wave current interactions here.
they could be, yeah. They could be I'm sure the kind of currents that we were seeing is probably enough to drive that Lanier, the wave current interactions. But yeah, it's difficult to say clearly because we don't have surface measurements of turbulence, nor do we have a great wave spectra for the ship. So unfortunately, Lanier turbulence is a little hard to infer from our measurements. But we have other instruments that other students are looking at. So we have very high resolution temperature measurements from a chain that had temperature sensors every 0.5 meters, so very high resolution. And so there's some other ways in which we need that. You can see these very convective eddies really clearly. So there's a student working on trying to see if that would be related to Lanier turbulence.
Can you go back? Go back. There was that diagonal descent of
Oh yeah,
what this? On the table.
this one.
Yeah, maybe this like this. There are red streaks which are
Oh yeah.
much higher. You can see.
Yeah, sorry, that is, we still have to correct some of these measurements. So there was like a thermistor chain that we deployed that had a weight that kept messing with the ADCP beam, so the current beam. So yeah, that's not real.
And your good data starts from a couple of meters, 4 meters.
Yeah, for the shear, it's about 12 meters. Same with the epsilometer turbulence, mostly because the surface is all ship weight, so we can't really relate that to actual ocean turbulence, or it is actual turbulence in the ocean, but it's driven by the ship. But we have a little bit better resolution in the temperature and salinity, just because you don't need to throw away as much data at the surface. So,
During all these measurements, ship is at one place or it's drifting?
it's drifting, yeah.
So over this period, how much would it go?
So it probably was getting measurements every 200 meters. So, well, maybe like 30, 40 kilometers. I do the math in my head, but something like that. Yeah. But what we usually used to do was to drift and then come back and drift
Okay, so
again.
you drift and every time you want to do the next measurement, you come back.
Yeah, so sometimes, there wasn't like a real, there wasn't a real timing, but that was sort of our attempt was to try and keep it to a certain distance and then come back.
Do you have data where you switched on all the engines? Ship without
No, yeah.
all engines off?
No, because we actually need a little bit of the ship thrust to have to do the profiling. But we probably could have done it by just got the current measurements. But yeah, we didn't.
So Emily had done that over the previous.
With the turbulence profile?
That was, no, I don't think they had this kind of instruments, but they allowed the ship to just drift.
Oh, yeah. We should look back into that data.
couple of days at a time, then they brought it back to the negative.
Yeah, I think that was the idea, but we still needed a little bit
And
of,
to maintain the orientation of the script with respect to vision, they still need some intensity in it. But just so that wire carrying the propeller moves away.
That's right.
yeah,
But
that's
you have clusters. She could have clusters which can maintain the orientation.
yeah, but we usually avoid, or they don't like us profiling right for the cluster of entangling problems. So we usually profile on the side of the ship to avoid that. Yeah, so sort of going back, which just looking at these turbulence scalings to try and see how the data compares. So this is our dissipation measurements for each of those four regimes scaled by the corresponding turbulence scaling for wind-driven wind-driven dissipation, and then for convective driven dissipation. So the wind-driven case fairly, and this is scaled in a log axis. So the vertical line here shows you the basically a one-to-one correlation between those two measurements. And so generally in the wind-driven case, those values are relatively similar. There's a little bit of overestimating by the scaling in the strong wind forcing cases, and slightly higher in relative to the measured dissipation is slightly higher than the scaling in the pre-monsoon and recovery case, kind of pointing to some of that wave-driven influence I was talking about. But then if you look at the convective case, as you go over time, and these dotted lines show you the boundary layer depth. So as the boundary layer is deepening, you can see that the relationship of the dissipation to the turbulence scaling is getting worse and worse over time. So basically, it's kind of an indicator that this turbulence is weakening relative to this buoyancy scaling. And that's a little bit weird because usually, and there are a lot of other turbulence researchers kind of rely on this being a fairly good one-to-one relationship to correct their measurements. And we spend a lot of time looking at this data and making sure it looks good. And we kind of came to the conclusion that this may be real. And so clearly it's showing that there's some process that's suppressing turbulence that we're not really capturing with the way that we are thinking about surface forcing on the boundary layer. And then if you kind of look at this for the full convective period, and then just kind of looking at this recovery and monsoon period, you can see that the scaling works and is relatively higher, as you would expect, than the wind-driven scaling. There's wave processes and relatively close to the convective scaling early in this diurnal deepening, and then weakens over time. So you sort of see two cases of that, the recovery and the monsoon. And that's something we're still kind of scratching our heads and trying to understand is why over the course of the day, you would see this weakening. And if you look at the pre-monsoon case, which is an example of this in a shallower boundary layer, you just see strong mixing relative to the scaling throughout. So that's still something we're trying to figure out. If people have advice or ways to approach this problem, I would definitely be open to hearing that. And now, so as I mentioned, we have these two periods where we have these diurnal bond layers, so these stratifying periods. And another thing we can look at is kind of understanding how those processes and entrainment in the upper ocean. And then we can do that by getting a measure of turbulent buoyancy fluxes from our measurements. And this only really works in the stratified ocean because there we can assume that because of the stratification, buoyancy also acts as a sink to turbulent kinetic energy. And so here, the production of turbulence is then either lost as a change in buoyancy of the ocean, so change in the density, or is lost as dissipation, so it's lost to heat by internal molecular processes. And that's described by what this ratio between how much of the turbulent production goes into the buoyancy loss is described by this value called the mixing efficiency. And if you kind of combine that idea and assume that the buoyancy is related to the stratification by some diffusivity, you can get a measure of parameterized eddy diffusivity. So this is basically diffusivity not at the molecular level, but diffusivity enhanced by turbulence as a relationship between our measured epsilon and our stratification of buoyancy frequency and squared. And all of this assumes a sort of Pickian diffusion, which is basically that these turbulent processes drive a sort of linear down diffusion of temperature and salinity gradients, from which you can get buoyancy. And so here, this is showing you buoyancy from surface measurements, and then buoyancy at the base of the boundary layer. So this is a measure of entrainment. So you can see positive buoyancy means the surface ocean is losing buoyancy, which tends to happen at nighttime. So this line here shows you midnight. And then it's negative during the day because it's gaining buoyancy. And similarly, you see relatively high buoyancy fluxes at nighttime, indicating that the boundary layer is losing buoyancy. So it's getting denser, deeper. And something interesting is that if you compare these two restratifying periods, is that the pre-monsoon has a much higher, generally higher buoyancy flux than the recovery period. And yeah, so you can see here, and that in particular is enhanced at nighttime. And so if you look closely at the diffusivity, which is really just a measure of mixing scaled by the stratification, you can see that it is particularly enhanced at nighttime, which corresponds to a time when this boundary layer is steeping and entraining into the temperature inversion. As you can see from this vertical temperature gradient, this is kind of the period where the subsurface becomes warmer than the surface. So you have a negative temperature gradient. And so you have this switching of where the water wants to go from hot to cold. And that water wants to go upwards. And so you have this sort of enhanced entrainment of this warm temperature inversion. And then moving on to the kind of recovery period, but you also have these sort of diurnal warm layers, but you don't have the subsurface temperature inversion. You have deeper nighttime boundary layers. So this boundary layer itself is deeper. You generally see just weaker entrainment and just a small peak right after the peak in heating during the daytime. And this is despite there being strong inertial shear at the base of the boundary layer after the cyclone. So after the cyclone went through, this is shear filtered just for the near inertial frequencies, which is typically thought to be a driver of entrainment and boundary layer deepening. But we see in this case that doesn't necessarily lead to higher fluxes. And then finally, sort of going back to this Warner paper, which was the study I showed at the beginning, kind of trying to understand the role of turbulent mixing relative to how much surface forcing was going into the ocean, so surface heat fluxes. And so in their paper during the summer monsoon, they found that turbulent heat fluxes were in the similar order of magnitude to this surface forcing and led to a net cooling of the ocean. So in our case, we really only see if we do that similar measurement. So look at just the turbulent heat fluxes computed with this equation here. for the base of the boundary layer, and this is the surface heat fluxes. And each of these values show you the net, the net integrated over those each 2-day periods. We see that the pre-monsoon is the only time where they're sort of an order of magnitude. And in this case, all of that heat is actually being mixed up. And it's corresponds and it's equivalent to kind of the sort of beginning of this cooling process that happens as clouds come in and start cooling the surface ocean in the pre-monsoon, which was really what we measured. And then as you go over time, you see that the turbulent heat flux is very weak relative to how much surface forcing comes in. And then the monsoon, we see sort of a return to potentially similar levels. And so what we can sort of conclude from all of this, I started out with these sort of 2 questions. What processes drive this boundary layer deepening over the monsoon transition? What we found was this was actually a difficult question to determine with our turbulence scalings, was sort of the general approach. These scalings generally seem to overestimate our dissipation rates. And that discrepancy between those scalings and our measurements, particularly the convective scalings, seems to increase over the monsoon transition. So something we're trying to think of what could be potentially suppressing mixing that we're not kind of capturing in this monthly model sense. And then the other focus of this was to, now that we kind of knew this discrepancy increase right after the cyclone and we entered the second sort of restratifying period, the second kind of question was how this influenced entrainment in the upper ocean. And we saw 2 case studies, one in the pre-monsoon, where you had this very shallow diurnal warm layer and very strong turbulent fluxes that were able to erode into the temperature inversion and lead to this net upward entrainment of heat, which was sort of a similar order of magnitude to the heat entering the ocean, heat cooling the ocean during this period. And then we go to a second case study where we have a very similar atmospheric conditions, but diurnal warm layers forming over a much deeper ocean. And in this case, we see a much weaker exchange with the interior ocean, despite there being these processes like the strong inertial shear that could be driving entrainment in the sort of general model that we think about. And so, yeah, happy to take questions, and also like to thank our funding source, the Office of Naval Research, and all of the ship and science crew that helped us get these measurements. So some of this is most of the science crew from the ship the ship crew that was part of our measurements, and then also the ICMSAT team and my 2 advisors' labs for all of their help thinking about these measurements and helping me process data. Thank you.
Questions? Any questions? Yes, Karan.
So, can you clearly see where the convection starts from the data? Is the way to measure heat fluxes? I understand. So, you have something like measure of when the convection would start.
Yeah, usually, so the usually when you kind of switch off the sun, basically, you should start seeing the formation of those convective eddies.
How long does it take?
Yeah, so in this case, you have both this process of these shear instabilities forming because of all of the trapped wind momentum, and then you have this convection forming. So in this case, you have these 2 processes happening at the same time. So I would say once the boundary layer is at its sort of deepest point, you should basically be mostly driven by convective eddies. So this should mostly be convectively driven. But the general way is to actually do this kind of scaling comparisons. But yeah, there seems to be some discrepancy in our measurements. Yeah.
And the conclusion, in a sense, is that turbulent dissipation is the highest when have more convection that shape the ones. That be a good way.
It's more that there's something that's causing a weakening of the turbulence over the course of this convective period that isn't what is typically expected when you look at dissipation profiles. So usually, if you look at dissipation profiles, they should match relatively well with the surface buoyancy flux depth across the convective period. It's usually there's a lot of papers that show that, but in our case, it seems to be.
What about the wind stress? You also compare.
Yeah, so the wind stress is this top plot, and it also is showing that it's relatively high as the boundary layer is deepening, and then it becomes weak relative to there's more, the measured mixing is higher than our scalings, which you would expect if there's both this sort of wind and wave processes happening, and is generally seen, and then you get to a period where it gets really quiet, which is what you see here. Like the dissipation gets almost, in some cases, 1 order of magnitude smaller than the our measurements. Oh, sorry, the scalings.
Any other questions?
General question. I've asked many. If you can go back.
Yeah.
There's some place you said 0.2 out of wind
Oh, yeah.
goes into internal, right? Somewhere in between.
And maybe this one.
This one.
Yeah.
Right. So you put in some energy into the ocean. I'm just looking at the wind.
Yeah.
And you said only 0.2 goes into the internal wave.
It is propagating, downward propagating.
Yeah.
So what's happened to the rest?
The rest of it goes into mixing the boundary layer and changing its density.
Right.
Or it's just like surface wave breaking. This is, I think, the part of the surface interaction we don't understand. Is how that wind energy goes into waves and then into the ocean. Like that process is still something people are trying to understand. But I think the general idea is that it gets all of that energy goes into the same. But I guess it would be an interesting experiment to see if you need that much to mix strong, like a static.
So I have a question from one of your earlier slides. Even before you showed the mixed layer biases from models.
Oh, I see. Yeah.
I think it's earlier.
Earlier. I think this might be the conclusion of this one, actually.
Yes. So if I look on the June, July, August, it's all red in the Bay of Bengal, which means mixed layer in the model is deeper than it actually should be. And it's all blue in the Arabians, is that right?
Mm-hmm. Yeah.
Which means mixed layers are shallower than
they should be.
So why is that contrast? Do you know?
Yeah, so I know the Bay of Bengal is a much more stratified basin. So there's a lot of issues. One is that we don't really get how much fresh water from rivers go into the basin. So we're not getting this process of this fresh water coming and stratifying the surface ocean and then causing these very shallow boundary layers to form. So we're not getting that process. The other is we generally just predict weaker stratification of the ocean and so, if you have the same amount of mixing with weaker stratification, you easily deepen your boundary layer, but that's not actually what we observe. And then the other is just the resolution of the bottle. So you get a very shallow boundary layer that forms in the peak. But this is the winter, this is the summer monsoon period, so that isn't actually a problem for this period. But yeah, so that is why you tend to see deeper boundary layers in the Bay of Bengal. And this, I think, is mostly there's a very strong wind curve, in the western part of the Arabian Sea. I think this is mostly that it's just not getting the boundary layer as a result of. But the errors usually are much more significant in the Bay of Bengal. It's much more stratified. Don't really capture that well in models.
Any other questions? Okay, there are no other questions. Yes, sorry.
So when you are measuring how do you actually, can you just give a brief explanation of how you actually measure this distribution rate? The kinetic energy distribution rate.
Oh yeah. So I don't actually have a slide for that, but the probe that we have, it has a piezoelectric beam. There's something in the middle at the bottom. But it basically when there's pressure applied on it, it bends, and that sends a voltage signal. And so
you're measuring like the derivative of the horizontal velocity.
Yeah.
So then to go from that to the dissipation rate, you're assuming something like isotropic turbulence, something like that.
Yes, yeah. So we assume that the turbulence is isotropic, so then you can simplify like the dissipation.
So what I wanted to ask is that you expect that to be a significant source of error. You're in a stratified system, so on.
Yeah, that is another question that I think people are still trying to figure out. I think the general assumption is when you're in this sort of TV turbulence state that turbulence should be isotropic. So this assumption is reasonable to make, but it may not necessarily be the case.
It should not be very difficult to actually measure if you have two different. I mean, you can in principle put two different probes and different actions and check.
So you can do that with with current measurements. So you can look at really look at the non-stress, see if you can with current measurements and do that kind of check of anisotropy. In our case, we really are only measuring. So in our case, we would have to have an instrument that's also kind of going in a horizontal direction.
Yeah, that I understand. You have to put inside instrument.
Yeah, but
It also has to move differently.
There's a tree falling. That's so you're assuming that as it's free falling, that there's a station getting discouraged. So so it is difficult to get multiple directions, but there's other instruments you can use to get at that question, which is not this.
Oh, but have people checked it that it's isotropic? I'm not from this field, that's what.
I honestly I don't know. These are like instruments that are still being developed in our lab, so it's still very early question whether it is actually reasonable assumption.
These have been put in the nose of gliders, that is ocean gliders. No engines. They just go down by gravity. And you can make it go at different angles. It's good. You adjust the balance here. The instrument side is smooth. 2, 3 meters. You put it at the nose of that glider. And so that is not in free fall. It has fins. So you can glide at a certain angle. So these instruments have been put. So
Yeah,
you're
that's
not
actually-
not looking just at free falling direction. When you are at it. But I don't know the results of this. Your question is, I don't have the answer.
I don't really, or I haven't read a lot of work thinking about that, but I've just heard from people that this is instrument development people that this is stuff they're trying to get measured.
Just feel money issue. Even those gliders, as they're going down, they still feel the effect of the surface wave. So they right bit to it is have very massive gliders, not the usual small ones. Those don't move that much in response to the These are very sensitive. That tip is
Yeah,
more or less what you have in your record today.
yeah.
That tip is just that. It's called and creating a voltage.
It's always a stress deploying it because we're always like, we don't want it to.
Very delicate.
Very delicate.
Some piezoelectric sense.
In BFD, when we measured, we had to that particular dissipation from like epsilon and shear flux. Like
That is, I think, for you, I think. Still no.
we measured epsilon 1 and epsilon 2, two dissipation rates we had, and one was not working. We took the epsilon 1, epsilon 2 we didn't take. So that both perpendicular.
That is for U versus Z and V versus Z. Nothing for W versus something.
Usually it's the same. Usually it's the same direction because you just want a redundant measurement. I don't know how it works in the BFD, but that's how
Yeah, but then how we can take only epsilon 1. But that the dissipation may need two components of shear.
Yeah, so
Right?
you assume it's also.
Your instrument will also free fall.
Yeah, but what I remember is we had two measurements of epsilon. One is one direction, one is on the
Yeah, but nothing measuring the horizontal derivatives of the.
yeah. That's but from okay.
Okay, thank you. So let's thank
Thank you.
Akita once more.